We looked at this function, x squared minus 1 over x minus 1, at the end of the last video. We found we had no trouble evaluating this in the limit that x approached 4, simply by using the limit laws. However, when we turned to x approaching 1, the story was different. And so this will be a function where we're going to have to move past the limit laws on to algebraic simplification. Before we do that, let's just check what the graph looks like. Now, I've put the functions that we're going to use in this video in already, just to not take up time during the video. So there, y1 is the function in question. When we look at its graph, well, when x approaches 1, it looks like its height approaches, I don't know, some finite value. We can use trace to narrow in on it. When x is 0.95, the height is 1.95. When x is 1.17, the height is 2.17. But of course, if we were to look into the table and ask when x is exactly 1, what is the height, we would get an error. Because, as we determined in the last video, just using the limit laws alone, we get an indeterminate form, namely 0 over 0. So the key in applying algebraic simplification is to eliminate, before we have to apply the limit laws, the offending expression. In this case, it's the x minus 1 in the denominator that creates the 0 in the denominator. And so the question we're always looking for when we're doing algebraic simplification is there some way to simplify the numerator so that it also contains a factor of x minus 1? Then we could cancel those factors before applying the limit laws, before things became a problem. Well, if you look at this, hopefully you'll recognize from your pre-calculus days, oh, those were the good old days, the difference of squares here in the numerator, x plus 1, x minus 1, and divided by x minus 1. Now, we're eager to cancel out the x minus 1's, but let's just take note of one key thing. And that is, again from pre-calculus days, we can cancel top and bottom, cancel numerator and denominator in every case except when the denominator is 0. In that case, we're not allowed to cancel numerator and denominator. Now, isn't that the very problem that we have right here, though? That the denominator is 0? Well, it would be, except that notice we're taking the limit as x approaches 1. And this is why it was key to the definition of limit that we talked about x getting ever closer up to c, some constant value, but never touching it. Because our definition of limit talks about never touching the point we're approaching in question, we can cancel these because these never become 0. Now we've, so to speak, tamed the function, and we can take the limit as x approaches 1 of x plus 1. We can apply the limit laws. Just the simple sum limit law works here. Limit as x approaches 1 of x, plus a separate limit as x approaches 1 of the 1 function. This limit is a known limit. This limit is a known limit. Our answer is 2. And recall that that's consistent with what we saw in the graph. Consistent, but remember, we could have never obtained definitive information by looking at the numerical approximations in the graphing calculator. Let's try something else. Try another one. Okay, here's an expression, clearly not a known limit. We'll graph it just to get some intuition about what we're looking for. And if you look in your y, you'll see that this function, I'm going to turn off the graph of the first expression now that we've dealt with that. We'll go down to this second one, turn it on, and we get a graph. Okay, in this case we're evaluating the height as x approaches 0. We can use trace to do that. When x is 0.95, the height is 8.9. When x goes down onto the other side. Let's see, we're getting closer to x equals 0, but it's still x positive. We've got 8.1. Now we're into x negative, and we've got 7.89. So something between 7.89 and 8.1 is our hoped for answer. It would certainly make our life simple if it was an 8, but that's not ours to say. We just have to follow where the limit laws and algebraic simplification take us. You'll see that were we to apply the limit laws, we would get an indeterminate form. First we'd apply the quotient limit law, then the difference limit law, then this squared we'd treat as a product limit law, and then a sum limit law. But in the end we would get 4 plus 0 squared minus 16 all over 0. That's going to give us 16 minus 16, 0 over 0. We've got an indeterminate form. That's not good enough, so we look for some algebraic simplification. Again, the expression that creates the problem is the x in the denominator, so we look to somehow isolate an x in the numerator so that we can cancel them before applying the limits. We'll FOIL this out. We get limit as x approaches 0. Again, I should have put limit as x approaches 0 in each of these. Limit as x approaches 0 of 16 plus 8x, that's adding 4x to 4x, plus x squared minus 16 all over x. Our 16s cancel each other out. We're left with a limit as x approaches 0 of 8x plus x squared over x. We can factor out an x from the numerator. We have 8 plus x remaining in the numerator. And now we'll do this cancellation. Again, think about this. Why can we do this cancellation? We certainly can't cancel these out if x equals 0. But the definition of limit talks about getting ever closer to the value specified but never touching it. That's why it's legitimate to cancel these out before applying the limit laws. Now we're left with the fairly innocuous limit as x goes to 0 of 8 plus x. We apply the sum limit law. 8 plus the limit as x approaches 0 of x. This is a known limit. It's 8. This is a known limit. It's 0. Notice what happens each time. We work the progression downward, stopping as soon as we've found something that works. Once we find something that works, then it allows us to simplify, in this case, from algebraic simplification. We could then apply the limit laws without getting an indeterminate form. And the limit laws, in turn, led us back to breaking the problem down to a set of known limits. And so we work the progression upwards and then back down. We'll try one more. I'm sorry, I didn't finally list our answer. So our answer is 8. Again, that's consistent with what we saw in the graphing calculator. So last problem. Hopefully you'll get the hang of how these work. Okay, well, this is our most complex expression yet. It's clearly not a known limit. Let's see what we get when we graph this. Again, I've put the function in. You can check that here. 1 over 2 plus x minus 1 over 3, if you scroll over just slightly. And when we graph it, we get, let's go down to that function. When we graph it, let's see, when x is 0.957, we get a height of 0.113. When x is just slightly larger than 1, we get a height of 0.110. So somewhere in there we expect a finite value, but it's fairly hard to judge simply looking by looking at the calculator. Let's see if we can't get an exact result by using the progression. The limit laws, of course, in this case, if we applied them, we'd use the quotient limit law first, then the difference limit law, quotient limit law, sum limit law, so forth. And we would get 1 over 2 plus 1 minus 1 over 3 all over 1 minus 1. That would be 0. We'd get 1/3 minus 1/3 over 0. We're going to get 0 over 0, an indeterminate form. The limit laws are not enough to get us to the answer we're looking for, and so we'll need to apply some form of algebraic simplification. Now this one looks fairly challenging because, again, what causes the problem in the denominator is 1 minus x. We'll need to somehow get a factor of 1 minus x up here in the numerator. I guess the starting point is to get a common denominator. Now you'll recall from pre-calculus that the way to get a common denominator is to multiply numerator and denominator of each individual term by whatever is missing from the denominator that would be needed to make for a common denominator. In this case, it's going to be that we need to multiply by 3 over 3, and in this case we need to multiply by 2 plus x over 2 plus x. That's all going to be divided by 1 minus x. Now we have a common denominator. We have 3 minus 2 minus x all over 2 plus x times 3. That result is itself divided by 1 minus x. And we still want the limit as x goes to 1. This might be a little intimidating to you, but remember that we can turn this division by something into multiplication by the reciprocal. So let's write that out. 3 minus 2, of course, is 1. So I have 1 minus x divided by 2 plus x times 3. And now I'll multiply by 1 over 1 minus x. Well, that gives us the desired 1 minus x factor. I'll just mention this last time again. We would not be allowed to cancel out these 1 minus x factors if we were dealing with, at any point, a value of x that equaled 1. But because the definition of limit was constructed specifically for this situation to mean getting ever closer to a finite value but never touching it, we can do this 1 minus x cancellation that allows us to proceed. We now have the limit as x goes to 1 of 1 over 2 plus x times 3. We'd apply the quotient limit law now. We'd apply the product limit law. We'd apply the sum limit law. And we would get 1 over 2 plus 1 times 3, 1 over 9, which, if you'll recall, in its decimal approximation is 0.111 and so forth. And that's consistent with what we got in the graphing calculator.